2.1, 2.2. So organized counting and the fundamental counting principle. So the goal here is to apply organized counting methods and the fundamental counting principle to solve problems. So I'm going to teach you how to count. And this is a branch of mathematics called combinatorics, and it's the idea and methods for counting, especially in complex situations. Okay, so it's an entire chapter on how to count and how to use some special methods for counting, especially counting large amounts of numbers, and when you're looking at different ways to count different outcomes or trials, we're going to use some special techniques and methods to do this. So I'm going to do this by example. So the first one here is Little Red Riding Hood is on her way to Grandma's house. From her house, there is one path going to a pond, one going to a field, and one going to a wolf's lair. From the pond, there are two paths to Grandma's house. From the field, there are three paths, and from the wolf's lair, there is just one path. Illustrate the paths from Red Riding Hood's house to Grandma's house with a map and a tree diagram. So I'm going to first start with a tree diagram, and a tree diagram is a useful tool for keeping track of all the possibilities in a situation. Especially in a situation where events happen in a particular order. Okay, and I'm going to just show you how such a structure can be used to count the number of different ways for Red Riding Hood to go from her house to Grandma's house. So I'm going to start off here on the left side here. I'm going to start off with Red Riding Hood right there. And we know that from her house, there's one path to going to a pond. So I'm going to just illustrate that by showing that we're going to draw a path to going to a pond here. And we know there is one path going to a field. So I'm just going to draw one branch of my tree pointing to a field. And I'm going to draw a third branch going to the wolf's lair. So I'll just draw a wolf down here and show a third branch going there. Now, the next part of the question says from the pond, there are two paths to Grandma's house. So I'm going to draw again two branches. So Grandma and Grandma again. And I'm going to show two branches extending from the pond to continue this tree diagram. And then from the field, there are three paths. So I'm going to have to show that there are three ways to get to Grandma's house. So Grandma, Grandma, and Grandma. So three paths, three more branches, 1, 2, 3. And finally, there is from the wolf's lair just one path to Grandma's house. So down here, I'll show here one more time Grandma and show one branch extending. So how many paths are there? Well, if I count the number of endpoints of my branches, I have 1, 2, 3, 4, 5, 6. I have 6 possible paths. Now, how do I show this using a mapping diagram? Well, it's really quite simple. At the start, I have Red Riding Hood. At the end, I have Grandma's house. So between Red Riding Hood and the Grandma's house, I have the wolf's lair, I have the field, and I have the pond. And I'm showing 3 paths, one for each. And then, out of all these 3 different places to go, they all connect to Grandma's house. And we know wolf's lair only has 1 connection. The pond has 2 connections, and the field has 3 connections. So I can show this mapping diagram like so. And I can indicate that there are 1, 2, 3, 4, 5, 6 ways to get to Grandma's house. So in part B, my answer to that, to either the mapping diagram or the tree diagram, they both yield the same number of possible paths, and that there are 6 possible paths. So there are 6 possible paths from Little Red Riding Hood's house to Grandma's house. Example number 2. Javon wants to buy a new smartphone. The brand he likes comes in 6 possible colors with either 2 gigabytes, 4 gigabytes, or 8 gigabytes of memory, and 64 gigabytes or 128 gigabytes of storage. How many different configurations of the smartphone are available to Javon? So we're told that we have 6 colors. We have 3 memory sizes to choose from: 2 gigabytes, 4 gigabytes, or 8 gigabytes. And we have 2 possible storage sizes. So you could draw a tree diagram to show all the possible outcomes. We can also use a little bit of mathematics as well. So I'm going to say here, for each color choice, there are 3 memory sizes. So if you had 6 colors to choose from, and you have 3 memory sizes to choose from, if I said 6 times 3, I would have 18 options. Why? Because for each color, I have 3 memory sizes. So it's 3 times 3 times 3 times, like 3 and 3 and 3 and 3 and 3. So 3 plus 3, I should say. So that's for each color that we have. So 18 options for just the colors and memory sizes. So even if you drew a tree, you'd notice you'd have 18 options by this point. And then I'm going to say that for each of these 18 options, there are 2 storage sizes. Okay, so that means, therefore, that for 18 options that I have for the color and the memory size, if I multiply that number by the 2 storage sizes I have for each option, I will have now a total of 36 options. So therefore, if I multiplied all the 3 numbers of outcomes for each choice, I can get a total count of 36 total choices or options. So 36, so therefore there are 36 possible, let's call it configurations. And this is often what new smartphone companies would do. They offer you options, different colors, different memory sizes, different storage sizes, and they may not have 36. Maybe they'll just go with the more popular ones, but there will be a number to choose from. Okay, so this leads us to what we call the fundamental or multiplicative counting principle, the multiplication counting principle. And this says that the total number of outcomes of different events with distinct choices is going to be equal to the m times n times p times dot dot dot. You're multiplying all the number of outcomes of each of the different events to get the total number. Okay, so m is the number of choices for the first option, n is the number of choices for the second option, and p is the number of choices for the third option, and so on, depending on the number of options that you have, number of events. Okay, so let's look at an example number 3. So a school band is looking into buying new band uniforms. The band committee is considering 4 different white shirts, dress pants in gray, navy, or black, and black or gray vests with the school crest. How many different designs for the band uniform is the committee considering? So you have so let's count this here. So we have 3 different pants. So let's number of shirts. So we have 4 different white shirts. Do we have any other shirts? No, so we're going to say 4 white shirts. So 4 shirts. N we'll say is the second option, so the number of pats. So we have 3 pats. And we have P, which is our third option, which would be the number of vests. So we have a black or gray vest, so we have 2 possible vests. So the multiplicative counting principle will tell us how many total choices or combinations of the band uniform we could be considering here. So if I take my values for M, N, and P and I multiply them, N times P, I will get 4 times 3 times 2, which is equal to 24. So therefore, the committee is considering 24 possible uniforms. Okay, let's look at example 4. They use the multiplicative counting principle to determine how many possible outcomes there are for flipping a coin. So if you flip a coin once, you only have 2 possible outcomes, so M equals 2. If you flip a coin twice, M equals 2 for the first outcome. The second event is the flipping of the coin the second time, the second outcome. And it's important to note that your second event does not depend on what happens in the first event. All we're just saying is the total number of outcomes, M times N, which is equal to 2 times 2, and that is 4. So there are 4 possible outcomes for flipping a coin twice. Okay, and I want to also do this, express these numbers as also as powers. So I can express 2 as 2 to the power of 1. I can express 4 as 2 to the power of 2. Now what about flipping a coin 3 times? Well, we have 3 possible events here. M equals 2, the first flip. N is our second flip, again the 2 options, and P is our third flip. Again, another 2 options come from that, or another 2 outcomes come from that. So my multiplicative counting principle says if I multiply all the number of outcomes for each event, I will have 2 times 2 times 2, which is equal to 8, which is also equal to 2 to the power of 3. What about 4 times? Well, now I'm just introducing another letter here. So M equals 2, N equals 2, P equals 2, and let's say Q equals 2. Multiply M times N times P times Q, and we get 2 times 2 times 2 times 2, which is 16, or as a power, I can express that as 2 to the power of 4. And N times you flip the coin, well, you're just multiplying 2 times 2 times 2, however many times, N times, so let's just say N times. Well, how do I find the answer to that? Well, you might see the pattern that it's simply 2 to the power of N is the total number of possible outcomes. All right, let's look at another example. So example 5, you roll a standard 6-sided die. How many outcomes are possible with one roll? Well, on a 6-sided die, I have every roll has 6 possible outcomes. So it's going to be 6 to the power of 1 for one roll, which is just 6. For 2 rolls, I have 6 to the power of 2, which is 36 outcomes. For 10 rolls, I have 6 to the power of 10, which is a really huge number. It's 60,466,176. So now you can sort of start seeing the power of counting principle. So n rolls, 6 to the power of n. So the multiplicative counting principle will tell you how many outcomes there are in 10 rolls without you having to count them one by one using a tree diagram or a mapping diagram. Just simply use the fact that each roll has 6 possible outcomes, and if you multiply that 6 10 times, 6 to the power of 10, you'll get the total number of possible outcomes, 60 million and change. Okay, so example number 6. A jar contains a red, a blue, and a yellow ball. A student removes 3 balls, one after the other. how many possible outcomes are there if the balls are replaced after each selection. Okay, so if you are going to make uh, 3 selections, so I have there are 3 balls. So the ball number 1, and again you have a choice of 3 for ball number 2, and again you have a choice of 3 for ball number 3. So for each event you have 3 possible outcomes, distinct outcomes. Okay, so the multiplicative counting principle will say to us m times n times p is equal to 3 times 3 times 3, which is just 27. So therefore, there are 27 outcomes. Now keep in mind this was when the balls are replaced after each selection. Okay, and that's really important to note. Okay, because the multiplication rule, the idea behind this rule, allows us to think of objects we can count. But regardless of what happened in prior steps. Okay, so each time we pull the ball in the second or third time, doesn't matter how many times we pulled it before, because we replace it after each selection. But part B, what happens if we're not replacing the balls after each selection? So let's look at ball 1. So in ball 1 we have how many possible outcomes? Well, we have 3. Okay, but if we took one out but we don't replace it, what happens? Ball number 2, well, we only have now 2 balls to choose from. And in ball number 3 that we draw, well, we only have now 1 left to choose from. So in our first event M, we have 3 outcomes. For our second event N, we have 2 outcomes. And for our third event, we only have 1 outcome possible, 1 ball left. So you just draw that third ball. So the multiplicative counting principle still applies. N times P, which is just 3 times 2 times 1. And this time you see that we only have 6 possible outcomes. So there are 6 outcomes when you don't replace the ball after each selection. Okay, example number 7 from a class of 25 students. In how many ways could 3 students be selected to attend a workshop, 1 as a speaker, 1 as a videographer, and 1 to take notes? So now here in this situation, we're going to say that we're selecting 3 students, so we can't just have 1 student act as both the speaker, videographer, someone taking notes, or 1 person to do 2 roles. No, we have 1 student for each of these 3 roles. So that means each event is going to have a changing number of outcomes. So let's say we pick a speaker first. We have 25 students to choose from for the speaker. And then now we have to pick a videographer. So after you pick 1 student to be the speaker, you only have 24 students left to pick for your class to be the videographer. And then if we pick a videographer, then we only have 23 students left to pick from to be our note taker. So that means if I have multiplied these 3 values, my multiplicative counting principle says that I have 13,800 possible outcomes. Or 13,000, right here, there are 13,800 ways to select 3 students to attend a workshop. Now you can imagine that drawing a tree diagram and listing all the possible choices to pick 3 students from a class of 25 would be very tedious, which is why we use things like the multiplicative counting principle to help us simplify our counting. Now let's talk about an indirect method. So a problem-solving technique for finding a quantity by determining another, often opposite quantity from which the first can be derived. In some situations, an indirect method makes calculations easier. So example 8, Leora, a triathlete, has 4 pairs of running shoes loose in her gym bag. In how many ways can she randomly pull out 2 unmatched shoes, one after the other? So in that case, order will matter. And in many different problems we're going to study, order may matter or order does not matter. But in this particular chapter, we're going to talk about order mattering, that order matters. And I'll try to make this concept less confusing as we go along. So to find the number of ways of picking unmatched shoes, you should subtract the number of ways of picking matched shoes, so matching pairs of shoes, from the total number of ways of picking any two shoes. Okay, so what are the total possibilities? Well, you have 8 choices to pick from your first shoe, and you have 7 choices to pick from your second shoe, because you reduce the number of choices by 1 after you pick the first shoe. You're not replacing anything. So there are 56 total possibilities. However, if you want the matching pairs of shoes, so if you pick the left shoe first, then, well, there are really only 4 possibilities to do that. And if she picks the right shoe first, well, there are also only 4 possibilities to do that as well. So if I add those two, 4 plus 4, I get 8. Or I can say 4, so there are 4 matches times 2 ways to do it. Because there are 4 matching pairs of shoes, and there's 2 ways to do it for each one, to pick a matching pair of shoes. So we have, that equals 8. So 8 ways of picking a matched pair. So out of 56 total possible outcomes, there are 8 ways of picking a matched pair. So therefore, Lyra can pull out 2 unmatched shoes in 56 minus the 8 ways to pick a matched pair. Well, that means 48 ways to pick an unmatched pair of shoes. It's kind of an indirect way of solving problems like this. Example number 9. Consider the possible arrangement of the letters in the word money. How many part A, how many different arrangements are there if there are no restrictions? So I'm going to just take these letters and say, how many ways are there to arrange these 5 letters? It doesn't have to spell a word. It could just be basically, how can I, switch in, around the letters that you see here in the word money, say M-O-N-E-Y. Well, in the first letter, you have 5 choices. Okay, M-O-N-E or Y. After you place that first letter there, in the second letter, you have 4 choices left to choose from. And then, so let's say, if you picked an M, you now have 4 left to choose from. Your third letter, let's say you picked an O for that. Now you have 3 choices left to choose from for your third letter. You picked another letter, you have 2 choices left to pick for your fourth letter. So you pick this one, and then you have 1 choice left for the fifth letter. Okay? It doesn't matter what you choose, you have these, this is how it works when you look at counting the number of possible outcomes left for each event or choice. So the multiplicative counting principle says if I multiply these together, 5 times 4 times 3 times 2 times 1, I get 120 arrangements. So there are 120 ways that I can mix and match and move in and around these 5 different letters to make something. Alright, so how many different arrangements are there if the first letter must begin with a vowel? So we only have 2 possible vowels here. We have O and E. Okay, so in the first letter, I have 2 choices. It can be O or E. And after picking O or E in my second letter, I have 4 choices left to choose from. My third letter, I have 3 choices left to choose from. And my fourth letter, I have 2 choices left to choose from. And my last letter, I have 1 choice left to choose from. So the total possible number of outcomes or arrangements are going to be, by using the multiplicative principle, 2 times 4 times 3 times 2 times 1, which is 48 arrangements. Okay? And part C, how many different arrangements are there if the first letter must not begin with a vowel? So if we're not going to begin with a vowel, well, you can have M, N, or Y as our first letter. So we have 3 choices. And then if we remove one of those letters, then we have 4 choices left for the second, 3 choices left for the third, 2 choices left for the fourth, and 1 choice left for the fifth. So the multiplicative counting principle says I have 3 times 4 times 3 times 2 times 1 is equal to 72. So I have 72 possible arrangements. Now, an indirect way of doing this would be to say, well, if I already calculated how many arrangements there are by doing the vowels, well, I just subtract them from the number of arrangements I can do altogether. So 120 total possible arrangements for all situations, minus the ones that start with a vowel, will leave me with the 72 that start with a consonant, meaning the M, N, or Y. So this is just a vowel only, and this is just M, N, or Y as the first letter. So there are, in total, 72 arrangements of doing that. And that ends our lesson for the first 2 sections of Chapter 2.